Hi everyone, in lesson 1-3, we are going to discuss continuity and behavior and limits. And in this particular video, our learning target is for students to be able to use limits to determine the continuity of a function. Now, if you have not watched video 1.3.1, in which I did some examples of continuity and also what limits are, you might want to go back and watch that at this time. In example 2, we're asked to identify a point of discontinuity. We're asked to determine whether the function f of x equals 1 over x minus 1 is continuous at x equals 1. Justify using the continuity test. If the function's discontinuous, identify the type of discontinuity as infinite, jump, or removable. Now, what we're going to do first is I want to analyze the domain of this function. If I'm going to analyze the function f of x, I'm going to go ahead and look at what its domain is first. Now, we've talked about how to determine the domain of a function algebraically, and I know with fractions, right? Fractions, we know that the denominator cannot equal 0. We can never divide by 0. So I'm going to say that x minus 1 cannot equal 0. Or this implies if I add 1 to both sides of the equation, x cannot equal 1. So what this is telling me is that my domain, because again, here's my number line, and I'm going to exclude 1 from my domain, right? I'm going to exclude 1 from my domain, and we are going to go from negative infinity to 1 union 1 to infinity. So we are excluding 1 in our domain, and the function is going to have either an infinite, jump, or removable discontinuity at 1 because 1 is not included in our domain. So my next step here is I know the function's discontinuous at x equals 1 because 1 is not included in the domain of the function. And so what I'm going to do is I'm going to go ahead and graph this function and go ahead and look at what type of discontinuity it might be. So looking at the graph of the function, I've graphed the function 1 over x minus 1, and this is the graph that was produced. And I can see that I have this break in the graph along an x value of negative 1. Okay, so if I'm looking at x equals 1 right here, there's this invisible vertical line at x equals 1, and I can see that there's a break in the graph that I would not be able to sketch this graph without lifting up my pencil, and I would have to lift up my pencil. This piece right here is getting closer and closer to an x value of positive 1, but never reaches it. Same thing with this piece. If I move from the right to the left, we're approaching 1, but never intersect x equals 1. So therefore, the function's discontinuous there. So I need to prove, not just by the graph and not just by the domain, but by using the continuity test, that this function is discontinuous. So using the continuity test, first of all, the first step of the continuity test is to show that f of 1 exists. Again, our function was 1 over x minus 1. And if I were to evaluate this function right here at x equals 1, I would get 1 over 1 minus 1, or 1 divided by 0, which is undefined. You cannot divide by 0, so there is no y-coordinate paired with an x-coordinate of positive 1. I can confirm that there is no y-coordinate paired with an x-coordinate of 1 by looking at the table of the function. So I went back to my graphing calculator and I'm analyzing the table, and you can see that at x equals 1, our function is undefined. There is no y value paired with an x value of 1, which also tells us that the function is discontinuous at x equals 1. And based upon the graph, on the previous slide, I'm going to say because as we approached 1 from the left and from the right, the function was headed downward or upward infinitely. We're going to say that it's an infinite discontinuity. And an infinite discontinuity occurs when you algebraically substitute in an x value that forces you to divide by 0. That creates an infinite discontinuity in the graph of your function. Okay, in example 2, identifying a point of discontinuity, we are going to determine whether the function f of x equals x minus 2 divided by x squared minus 4 is continuous at x equals 2. Now we are going to justify our answer using the continuity test as well as determine what type of discontinuity the function may have, whether it is infinite, jump, or removable. Okay, just like the previous example, I'm going to analyze what the domain of this function is, and anytime I have a fraction as part of my function, I know that the denominator cannot equal 0. So right off the bat, I'm going to determine what the domain of this function is, and I know that x squared minus 4 cannot equal 0, which tells me that x squared cannot equal 4 if I add 4 to both sides. I added 4 here and here. Negative 4 and positive 4 would cancel out. 0 plus 4 is 4. And then I'm going to square root both sides, which tells me that x cannot equal plus or minus 2. Because when I square root both sides, I put a plus or minus in front of my square root. So x cannot equal 2 or negative 2. So I have two places where this function is discontinuous. Okay, if you look at this further, this function could also be written as x minus 2, and on bottom, x squared minus 4 could be factored into x minus 2 and x plus 2, which further supports that right here, x cannot equal 2, and right here, x cannot equal negative 2. Because we don't want either of these factors to equal 0 on bottom in our denominator. Now, I could simplify this function because I have a factor of x minus 2 on top and a factor of x minus 2 on bottom, which tells me that at x equals 2, we have a removable discontinuity. And at x equals negative 2, since that's still left on bottom, and I'm going to end up dividing by 0 if I substitute negative 2 in for x right here, I'm going to say at x equals negative 2, we have an infinite discontinuity. Now, I'm going to support my answers. I'm going to provide a graph and a table on the next slide, as well as go through the steps of the continuity test to show that the function is discontinuous at both 2 and negative 2. Okay, looking at the graph of our function, first of all, looking at the table, we can see that negative 2 is paired with no y value, as well as positive 2 is not paired with a y value. So that is telling us or indicating to us that the function is discontinuous at negative 2 as well as at positive 2. The function is discontinuous. Now, if you were looking at tracing the graph, though, if I trace this piece right here, I'm not doing a very good job of tracing it on my iPad, but you can see that if I trace, this is going downward, and I would have to lift up my pencil to then begin tracing this piece of the function. And where I lift my pencil is at an x value of negative 2. So I'm going to say that negative 2 is an infinite discontinuity because right along the graph here, as I approach negative 2, right here, my y value is approaching negative infinity because the graph is pointed down. And as I approach negative 2 from the right side of the graph, I'm going to say that our y value is approaching infinity because the y values are increasing or moving upward. So I know that at -2, we have an infinite discontinuity, which I showed on the previous slide, or discussed on the previous slide. It's an infinite discontinuity, but nowhere does it look like on my graph that at x equals 2, it doesn't even look like the function is got a break there. I wouldn't have to lift up my pencil at x equals 2, but the table is telling me that the function is discontinuous at that point. So what happens here, if I erase this, is that at +2, you have an open hole on the graph. At x equals 2, there's a hole, which is also considered a removable discontinuity. And it's removable, remember, because we had x minus 2 on top, and then when we factored our denominator, x squared minus 4 factors into x minus 2 and x plus 2. Well, these x minus 2's cancel out, removing the discontinuity and putting a hole there in the graph to represent that removable discontinuity. Because if I just simplified my graph or my function or equation into 1 over x plus 2, then I would never know that there's a hole at x equals +2. So that hole needs to be on the graph to show that we've canceled out these factors of x minus 2, and we have two places where our function is discontinuous. This is a removable discontinuity. Now, what I need to do on this slide is to show, using the continuity test, that the function is discontinuous at -2 and +2. And since I have two different x values where the function is discontinuous, I have to do the continuity test twice. Okay, so using the continuity test, I'm going to abbreviate continuity. Over here for x equals 2, in step 1, if the function was continuous at 2, f of 2 would exist. Well, based upon our table on the last slide, at 2, our function was undefined. Now, if you don't believe me, f of 2 equals 2 minus 2 over 2 squared minus 4. I'm plugging in 2 into the function. Again, the function was x minus 2 over x squared minus 4. And if I plug in 2, I get 0 over 0. And since we can't divide by 0, that function is undefined at 2. Okay, we're done with the continuity test for this part because the function does not exist at 2. So that tells me that we have what's called an discontinuity. And it's going to be a removable discontinuity. And at x equals -2, if I test that out, I'm going to first determine f of -2, which on our table told us it was undefined. And if I just second that up with checking what the table had, I have -2 minus 2 over -2 squared minus 4, or -4 over 0. Because -2 squared is +4, 4 minus 4 is 0, which dividing by 0 means that it's undefined. So the function is discontinuous at -2, and that is going to be what's called an infinite discontinuity because we were dividing by 0 here. Here, this was not an infinite discontinuity, only because we had 0 on top and on bottom. Here, we have 0 just on bottom, and we can't divide by 0, which creates an infinite discontinuity. In example 2, check for understanding. I would like you to determine whether the function f of x equals 1 over x squared minus 1 is continuous at x equals 1, and justify using the continuity test. If discontinuous, identify the type of discontinuity as infinite, jump, or removable. You have 4 choices. A, f of x is continuous at x equals 1. B, you have an infinite discontinuity at x equals 1. C, you you have a jump discontinuity at x equals 1, or D, you have a removable discontinuity at x equals 1. I would like you to go ahead and work out the solution to this problem. Begin by graphing the function and providing a table, and or looking at the domain of the function, and then go through this 3 steps of the continuity test as needed to determine whether the function is continuous or discontinuous at 1, and then if it is discontinuous, what type of discontinuity it would have. And you have 3 choices: infinite, jump, and removable. So go ahead and work the problem out and then submit your answer when you're finished.